Right. I think everyone can hear me, right? If you have any issue with the audios, please let me know and use the chat box. Right. Just take down the topic linear momentum conservation. Linear momentum conservation. This is under Newton laws, and this is one of the most important lessons, right? As a physics students, you must have 100% of understanding of this linear momentum conservation, right? And if you have any issue, please let me know in the chat box, right? The tut we are discussing today is posted on the group. I think everyone has downloaded that. If not, please download it from the group, right? Okay. Right. So at the previous classes, we discussed about Newton laws. So what happens when a force is applied? When an unbalanced force is applied on a system. So obviously, when a force is applied, those systems gain the acceleration, right? It could be a system or it could be a just an object. Those gets accelerated. So in this lesson, what we are going to talk is what happens when at the absence of force, absence of unbalanced force. So at the last class, we discussed F equals ma. Then the another equation is this one, right? So this F is unbalanced force. F is unbalanced force. This is change of momentum. If there is no unbalanced force, there cannot be a change of momentum, right? So that is what we are talking about in this lesson. If F is 0, change of momentum also must be 0, right? There's no change of momentum. So if there's no change of momentum, that is what we call momentum is conserved. Conserved means constant. Constant means no change. So simply, linear momentum conservation means if there is no unbalanced force, momentum cannot change. So that is obvious, right? In order to change the momentum, there must be an unbalanced force. So if there is no unbalanced force, linear momentum must be conserved. Conserved simply means does not change, right? That is what it means. Just take this down, take this sentence down below the topic. If an unbalanced force, take it down, if an unbalanced force is not acting on a system, is not acting on a system, its momentum is conserved. Its momentum is conserved to a certain direction. Its momentum is conserved to a certain direction. Okay. So it is obvious, right? It is obvious. If there is no unbalanced force, momentum cannot change. Momentum means mass times velocity. If velocity does not change, momentum cannot change. So it is obvious. But as for an example, we apply this principle mainly for collisions. Then we are going to apply the same principle for explosions as well. Mainly collisions and explosions, we are going to apply this principle. But for under any circumstance, this is true, right? This is a universal truth, right? So for collisions, for an example, I can say if there's a mass m1 and mass m2 and they have velocities v1 and v2, v1 is larger, right? Then they collide. Let's say they collide here. So you know that as they collide, what happens? Forces are applied. Let's say this is A and this is B. A force is applied on A by B. So this is that force on A by B. Then the reaction force is applied on B by A. On B by A. So those are action and reaction forces. So due to those forces, the velocities of these objects can change. So let's say its velocity changes to v3, and for the other object it changes to v4, right? So you can say there is a change of momentum, right? There is a change of momentum. Why is there a change of momentum? But previously I told you that there cannot be a change of momentum, right? If you consider each mass, not the whole system, if you consider like only m1, obviously its momentum changes because there's a force acting on that. At this instant there's a force acting, so the momentum changed. Obviously forces are applied when we consider only one object, right? But what happens if you consider the whole system? Whole system means both objects at the same time. Then these two forces cancels off. When you consider the whole system, these two forces cancels off. Understood? So now, due to the collision, there cannot be an external unbalanced force. But that is true only if you consider the whole system at once, right? You cannot consider each object and say momentum is conserved. When you consider the whole system, usually two objects, right? Whole system, then there is no force. If there is no force, there cannot be a change of momentum for the whole system, right? So that separation, I mean, choosing the system is very important, right? Choosing the system is important, right? Then what can we say? So now we know due to the collision, there is no external force acting on the system due to the collision. Now what can we say? Here the total momentum. Momentum is a vector, right? So always have to consider a positive direction. So to this direction, we can consider any direction. Let's consider this direction. What's the momentum? Total momentum? m1 v1, momentum here, plus m2 v2. So this is total momentum before collision. Before collision, right? then that momentum should be equal to the momentum after collision. So what is the momentum after collision? mvv3 plus m2v4. So because there is no external force acting here, when you consider the whole system, you can put equal sign here. So what does this mean? Momentum before collision, right? Before collision equals momentum after collision. And we consider this to a certain direction, right? So this is very obvious. It is not hard. It is very obvious because there is no force. But if you consider individual objects, not the both objects at once, if you consider one object, obviously there is an unbalanced force. But if you consider the whole thing at together, there is no unbalanced force. If there is no unbalanced force, there cannot be change of momentum. So the initial momentum is equal to final momentum. Initial momentum means before collision momentum equals after collision momentum. Understood? Right? But that is true for the whole system together. Right. Take this down and thumbs up. Take this down and thumbs up. No, we didn't do this part earlier, right? Earlier we didn't do this. We did impulse. I sent you a recording. That is a different topic, impulse. Yeah, it is a different topic, right? This is a different subject. You have to understand the difference there. Take this down and thumbs up, right? Once you take it down. You must understand the theory part 100%. If not, let me know, right? Did I send you on this one? Let me check. No, we didn't do this. We didn't, right? That one is kind of similar to this part. Similar to this part. But the theory behind it is different. I have discussed. I have discussed the theory part as well in that. Recording, at the last part of that recording, there's this theory part. I have already discussed that. Uh, I have already discussed, but that was on the recording. I thought that recording doesn't include this part. Today we will be doing somewhat more advanced questions, right? On this one. Just to recall you the stuff, get the tutor and just try the first question, first MCQ. Then I'll move on to more advanced questions, right? In the recording, yeah, we have discussed this theory, but it is okay if, just to recall this one again. Try the first question. Try the first question and send me the answer. No, it is recording. Try the first question and send me the answer. First, you can draw a sketch, right? Let me know if you have an issue. The speed of the bullet is, take it as 450 meters per second. That is the speed of the bullet, right? Take it as 450 meters per second. It is not given. Take it as 450 meters per second. So that is before the collision. After collision, it is 1.5 kilogram with the bullet. Has a velocity v. So you have to find v. Okay. So total momentum before collision is what? 450 times 0.1. This is at rest, so it doesn't have a momentum, 0. Equals after collision, you can consider bullet and the block as a one object. It has a v velocity. So this is before collision, this is after collision. So this is 45. When you multiply 45 equals 1.5. V equals 45 divided by 1.5. So it is 30. That is 450 divided by 15, right? So it is 30 meters per second. That's the velocity here. Yeah. Third one is the answer. If you have any issue, let me know. Then try second question. Second one. we'll just do a few questions, right? These questions were in the previous tute as well, just to recall you, okay? Then we'll move on to more advanced question after that. Just try the second question and send me the answer. This question is in the previous tute as well, right? Doesn't matter. Okay, so there is this object, 3 kilogram. It has a mass 3 kilogram, and it is moving at v. Then it explodes. It explodes into two parts. One part is 2 kilogram, another part 1 kilogram. To the same direction, it moves at 1 v over 2. What they ask is velocity of a small part. Let's say that is u. Okay. So here, this is an explosion, right? At an explosion as well, there's no change of momentum. Why is that? So when an object explodes due to internal, right? When there's an internal explosion, these two forces, when you consider the whole object as a one system, these becomes internal forces. Due to internal forces, total momentum of the system cannot change. There's no force on the system. So the total momentum cannot change. So this is momentum before explosion. So it is 3v, right? To this direction, 3 times v. After explosion, also momentum should be 3v. Meaning it should be same. So here it is 2 times v over 2 plus 1 times u. Right? Now you just have to simplify this. 2 cancels off. 3v equals v plus u. Then u is equal to, take this v to the other side, 3v minus v. So it is 2v. Right? Fourth one is the answer. Yeah, correct. Fourth one is the answer. Right. Try 11th question. 11th question. It is not discussed in previously, so we'll try 11th question. Try that. 11th. Have you done that before? Okay. Just now, right? Right. Then try not 11th one. Try 15th question. 15. 15, right? So that is the exam question. Somewhat complicated. We'll try that. Try 15th question. You better draw a sketch before trying that. The sketch given. Just quickly draw the sketch, right? Doesn't have to be nice and perfect. Just quickly draw this sketch. So the difference here is there are three objects, right? But usually we can only apply linear momentum conservation only for two objects. Only for two objects at a time, right? At a time, only for two objects we apply it, usually. But this has three objects, right? This has three objects. Just first, I'll give you a minute, just try that first. Then I'll explain. This is an exam question, right? Okay, right. Listen now, right? Listen now carefully. This is a good question, so listen now, right? You can try that once I explain this. Okay, so here you are going to correctly apply linear momentum conservation, okay? But you can only apply that to two objects at a time. That is the normal procedure, right? So we are going to follow that. So you are going to choose two objects. First, I am going to choose this one, the ball and the child with the trolley. This whole thing and the ball. Let's say A, this whole thing is A and ball. This is the system we going to apply momentum conservation. So what is the first case? Child at A is just holding the ball. Just holding the ball like this. Then he throws the ball. So what are the two cases? So as he throws the ball, he is putting a force on the ball, right? So he is pushing the ball. This is the force in order to push the ball. Then the ball also is applying a force on the child. Understood? Boy is pushing the ball and the ball also is applying a force. So those are action and reaction forces. When you consider that together as one system, these two forces cancel off. Now there cannot be change of momentum of the system. Therefore, what should happen? Momentum before throwing the ball should be equal to momentum after throwing the ball to these two. So before throwing the ball, what's the momentum of the system? This system. 0, right? Child is just holding the ball. Nothing is moving. So for these two, total momentum is 0. Then this should be equal to after throwing the ball. After throwing the ball gets a momentum, that is mv. Let's say the trolley with the child moves to this side at v1. Since it is to opposite direction, you can consider that to be mv1. I think you understand, right? So this is before throwing the ball. This is after throwing the ball. Ball gets the momentum to this side. Child gets the momentum to the other side. So it is negative. So 0 equals to this one. So this is the system we considered. Understood? You have to understand the theory, right? You don't have to memorize this stuff. The more questions you do, the theory must be gets clearer and clearer, right? Otherwise, doing the question is useless if you clearly does not understand the theory through the question. Okay, right? So this is the first case. So what they ask is velocity of A. So you just have to subject v1, that is v1, right? Take it to other side. So v1 equals mv divided by capital M. Actually, the velocity of v1 is, I got a positive value. Positive value meaning this direction is correct. You can show that as a negative answer there because it is the opposite side. That's what is shown here. So this is for one case, right? Then what is the another case? Let's say here it is B. Child at B. What happens? Child at B catches the ball. Then you can consider that to be another system. So there is the ball moving to this side and the child at the other trolley catches the ball, right? So the moments are before catching the ball and after catching the ball. This is the system. This is the system, right? So what happens when as he catches the ball hits the child on B. It causes a force on the child to this side. Then there's a reaction force by the child on the ball. So these are action and reaction forces. These two cancels off as you consider the ball and the B together. These two cancels off. So there cannot be a change of momentum for the whole system. Whole system means the ball and the B. B means a child, right? Understood? So what happens? Momentum before catching the ball is equal to momentum after catching the ball. So what is the momentum before catching the ball? That is, the ball is moving, right? The ball is moving, child is not, before catching the ball. So the momentum should be m times v. Child is at rest. After catching the ball, the child is holding the ball. Child and the ball is moving at a one velocity. Let's say that velocity is v2. Now the ball is on the child. So both ball and the child has the same velocity. So m plus capital M, you can consider that to be one object, child and the ball now. times V2. Now just substitute V2. I mean subject V2. MB divided by simple M plus capital M. That is V2, right? And the direction this side. So in the answers, they have said this to be minus, considering other direction to be positive, right? So what should be the answer? Third one, I think. Third one, right? If you have, yeah, that's the explanation there. The answer should be third one. Take it down, and if you have any issue, let me know. This is a very good question to fully understand this theory, right? The purpose of the doing questions is understanding the theory, right? Take it down and thumbs up if you have it. If you have no issue, thumbs up. Take it down. Yeah, sure. So as the previous question, when explosions happens, it is not always to opposite directions. If there's already a velocity after explosion, also there can be a to the same, can be to the same direction, right? But if they were at rest, it should be to opposite direction. I mean, I'm explaining a previous question, right? Okay, I'll explain again, right? So in this question, you can 100% understand the theory. That's why I'm taking time here. There are three objects, right? So it is not convenient to apply momentum conservation to three objects at once. So in those cases, you have to choose only two objects, one at a time, two objects at a time, right? For the previous case, A and the ball, these two are the system I'm considering. These two are the systems, right? So what's the previous case? Child is holding the ball and he throws the ball. As he throws the ball, child is putting a force on the ball to this side. And the ball also is putting a force to the other side, right? Then those two forces cancels off. Then what happens when you consider these two together, the ball and the A, momentum cannot change. Why? Because there's no external force. Those action and reaction forces cancels off. No external force, right? So what should happen? Before throwing the ball, momentum before throwing the ball, 0. He is just holding the ball, is equal to the momentum after throwing the ball. So this is the momentum after throwing the ball. This is the momentum of the ball, and the child backfires, right? He is thrown back. So when you throw something to this direction, you are pushed to the opposite direction, right? So this pushed to the opposite direction at V1. Then you just found V1. After that, it is just a simple calculation. So that is one scenario. Now A has already thrown the ball. Then B catches the ball. B catches the ball. So what happens when B catches the ball? Ball hits the hand, right? As it hits the hand, a force is applied on the hand. By the ball on B, there's a force applied on the hand. You know that every force has a reaction force. So the ball, then there's a child here. Force is applied on the child as he catches the ball. Then the child also applies a force on the ball. But when you consider these to be together, these two forces cancel off. Therefore, there cannot be change of momentum. When you consider these two together, then using that, I just applied linear momentum conservation. So what is before catching the ball? B is at rest. Ball is moving. What's the momentum? mv. This is before catching the ball. After catching the ball, now the child is holding the ball, right? He already has caught the ball. Child and the ball moving together now. So you can say now the mass is m plus capital M. And let's say velocity is v2. So this is that equation. Then you just have to subject v2. Now you get simple mv divided by simple M plus capital M. Understood? You can revise this question again, right? Then you will clearly understand the theory. So these are exam questions, right? So you have to understand in the exam, they check whether you have an in-depth understanding of these theories, right? They are not, all the questions are not like that, but there are many questions that they check whether you have an in-depth understanding of those theories, right? Okay. Then there's another good question that also an exam question, 23rd question. Try that first. I'll explain. This also is a very good question, right? To understand the theory. 23rd, try that. This is negative. Negative means it is to denote that it is moving to opposite side. That is just to denote that, right? Understood? You can show that using an arrow as well. But if you put a negative sign in the answer, it is just to denote that, right? It is moving to opposite direction. Okay? You can show the same thing using arrow as well. Right, try 23rd question. That also is an exam question, 23rd. Okay, let's see. 23rd, an object with mass m moves along x-axis. So y is here, x is here, right? So mass m moves along x axis. Then what happens? Breaks into two identical parts. Then one of the part moves parallel to y axis. Okay? One part. So this is before explosion, right? Before explosion. Then you need after explosion. So in an explosion, momentum cannot change for the system, right? Momentum cannot change, you know, because those are internal forces. Momentum cannot change. So what they say is after explosion, obviously one part moves parallel to y and the velocity is given as v. Here the velocity also is v, right? Then there's another part, another m over 2. So what they ask is to which direction does it move? We don't know the direction of this part, right? Direction of this part. The only thing you have to consider is that momentum does not change due to this explosion. That's all you have to consider. Momentum does not change. Can anyone guess the answer before explaining? I'll explain. What could be the answer? So I just explained the question. So once you understood the question, okay, let's see. Right. So an explosion happened, right? Due to explosion, there cannot be a change of momentum. I mean, total momentum of the system must be conserved. Cannot change the momentum. That is true for any direction. True for any direction, right? First, I'll think about the x direction. This direction. What's the momentum to this direction? Before explosion? mv, right? That is mv. Now what's the momentum? After explosion? After explosion also, momentum must be mv to this direction. Half of the object moves to y direction. So this part cannot create a momentum to this direction, right? Because they already have said this object part moves to y direction. So this cannot have a direction to this side, right? Momentum to this side. Because already they say this moves parallel to y, right? So mv, let's say this moves to this side at v1, has a component v1 to this x direction. So this mv, this momentum cannot be lost. So in order to create this momentum to this side, this must have a velocity to this side. another part. And also it must have velocity to this side as well. So this has two velocities. So when you consider x direction, mv equals, this doesn't have a momentum to that direction, but this has m over 2 times v1. So what's the value of v1? mm cancels off, v1 is cross multiplied, it becomes 2v. Understood? Now momentum to this is, x direction is mv. Here v1 must be 2v. So when you multiply these two, m over 2 times 2v, it becomes 2 mv to this direction, x direction. Now to s direction, momentum is conserved. You could do that without doing any calculations as well, right? Understood? To x direction, momentum is mv. After explosion also, momentum must be mv. Only way that can happen is this velocity must be 2v. So when you multiply 2v by m over 2, momentum becomes mv to x direction. I think you understood that. Okay. Now x direction is resolved. After that, you have to think about y direction. To y direction also, momentum must be conserved. So before explosion, what's the momentum to y direction? Before explosion? 0, right? To y direction, momentum is 0 before explosion, because it is not moving to y direction, right? Either positive or negative y direction, object is not moving. So the momentum to y direction must be 0. After collision also, momentum to y direction must be 0. Why? Because momentum cannot change. Okay, let's apply equations. So before explosion, momentum is 0 to y direction. Then after explosion, what's the momentum to y direction? Now there's this m over 2 and v2 upwards. Then you have to think about this one. Minus, that is moving to opposite direction, m over 2 v2. Here you need to find v2. Then you can divide the whole equation by m over 2. Then v2 is equal to v. Now we have found the velocity components v1 and v2. v1 is 2v, v2 is v, right? In order to find the direction, you need to find the resultant of these two velocities. Resultant of these two velocities. If you want, you can draw a rectangle. So 2v to this side, v to this side. So this is the direction. This part has to move. So this should be a acute angle, right? Less than 45 degrees. Understood? This should be less than 45 degrees. So the answer should be what? Second one, right? Answer should be second one. Okay, answer is second one there. Take it down, and if you have any questions, let me know. You have to again and again check these questions, right? These types of questions. These clearly, you can have an in-depth understanding of these theories. These are not that hard, right? Once you understood these. But Many find these somewhat complicated questions. Take this down, and if you no, there is no rule that the pieces has to go perpendicular to each other, right? There's no such rule. It is not a principle, right? The object, there can be many ways the exploded parts move, right? The parts can move like opposite direction, perpendicular, but it depends on the question there. The only rule that follows is momentum needs to be conserved. That's the only requirement there. In order to fulfill that requirement, the direction can be any direction, right? It depends on the question. Did everyone take this down? Or if you have any issue, let me know. Thumbs up if you have taken this down. Right. Then try 30. 30, right? MCQ 30. That also is an exam question, but it is somewhat easy. But try that 30. I'll give you some time. That also is regarding explosions. It is not hard, right? You can actually do it on by yourself. 30. For 30 as well, momentum is conserved to y direction and to x direction. That's what you have to consider. In the 30th question, there's a problem, right? The question is misplaced there. Do you see the 25th question? The explanation for that graph is at the 25th question, right? The question is misplaced. Got it? The explanation of the question is at 25th. The image is at 30, right? It is misplaced. So there's the object at O, then that object explodes. That object explodes, but the explosion happens under momentum conservation, right? Because it is an explosion. One piece is found at A, that is 6 gram. Let's say there's another piece at B, let's say MB, then another piece at C, let's say MC. MA is 6 gram. So you have to find these masses in order to find the mass of object before explosion. 3 pieces, right? There are 3 pieces. Consider momentum conservation to y direction and x direction separately. I'll give you a minute to try that. Let me know the answer. So if anyone got the answer, let me know. Okay, right. Let's see. Okay. Now listen, right? Now listen. Okay. There was an object at O, let's say a bomb. So it explodes into three parts, and you have found the locations of those parts, right? So using momentum conservation, you can find the mass of the initial object. Mass of the initial object. These are real world applications, right? So you know that when there's like a bomb explosion in like criminal investigation operations, they do these types of stuff, right? When there's a bomb, they literally apply linear momentum conservation, right, to in order to find the pieces of the bomb and from which direction it is landed, in order to find those, right? They really apply these cases, right? These are real world applications. Okay. So what should happen? What's the theory? First, think about x direction. X direction. Momentum is conserved. So before explosion, the bomb is at rest, right? Nothing is moving, so momentum is zero before explosion. After explosion, what has happened? This has moved 2 units, meaning this had a velocity 2, 2 velocity, right? I mean 2 ms minus 1, let's say. So to this direction, velocity 6 gram times mass is 6, velocity is 2 to this direction. That is from A. Then if you think about B to x direction, there is no movement of B. So from B to x direction, there is no velocity. It has moved perpendicular to x direction, right? Only. Then think about C. C has moved to this direction 3 units. Let's say the mass of 3 is mc. Because it is opposite direction, minus m3 times 3. So from this equation, you can find mc. So this is 12. 12 equals 3 mc. So mc is equal to 4 grams. We found mc. Then you have to find mb. To find that, you have to apply this to y direction. So if you apply that, A has no movement to y direction. Only C and B moves to y direction, right? So what about, it has moved 2 units. C has moved 2 units to y direction. And 1 unit to negative y direction, B. 1 unit to negative y direction. And this is after explosion. Before explosion, to y direction also, momentum is 0, right? Bomb is at rest before that. Then you can simplify that. We already found mc to be 4 gram. Then substitute it here. Minus mb. Take mb to other side. So mb is 2 times 4, 8 grams. So now we know ma 6 gram, mb 8 gram, and mc 4 grams. You just have to add these masses. So you can find the mass of the bomb. So that is 18 gram, right? Yeah, correct. Everyone understood? Thumbs up, right? You can take it down. If you are taking it down, thumbs up. Once you take it down. Let me know if any issue. Everyone, if you have taken it down, thumbs up. So what about others? Right. Then try the question. I'll give you a normal question. Try 37, 37, and let me know the answer. That's a easy question, right? Uh, 37. Let me know the answer. Yeah, perfectly elastic collisions, right? At the previous the recording also we have discussed that when it is a elastic collision, what happens? When it is elastic collision, uh, kinetic energy is also conserved, right? Kinetic energy is also conserved. So without any calculation, you should be able to say the answer. So when these collides elastically, what happens is they change their velocities. They just change their velocities. Uh, you have to know this one, right? Otherwise, the calculations gets, it is very time consuming to do the calculations. So what happens is this stops, meaning this gets velocity 0 and other ball gets velocity 5 meters per second. So this is what happens after collision. Okay, so that always happens. For perfectly elastic collisions, they exchange their velocities. You have to remember that, right? So it becomes 0 and 5. Okay. Then try 38. What's the answer? 38. Here. Yeah. Here also the same thing, right? So this is perfectly elastic. Then what happens? This mass gets 5 to this side. And the other mass gets 2 to this side, right? They just exchange velocities. So to opposite side, you can say that velocity is minus, negative. To this side, you can say 2. So the answer should be minus 5 and 2. Second one, yeah, correct. Then try 40. 40, right? Let me know the answer. So usually you have to know this stuff when it comes to collisions. You can apply equations and find these as well, but it is very time consuming, right? Not suitable for doing MCQs. Right, try 40. Let me know the answer. Right, let's see. There's a mass M1 and M2. This is at rest. Okay, so this also is perfectly elastic collisions, right? So you have to remember these qualities, right, as they collide. So after collision, if this is smaller, think think this M1 as a very small object, small mass. So what happens? It collides and bounces off. This could move to this side, right? So what happens? M1 moves to after collision if this is very small, right? So when you get questions like this, think about the extremes, right? Then in for most questions you will get the answer there. They just say this is slightly small, right? M1. But think that this is very small compared to this. Then you can think about what could happen, right? So when collides, if this is very small, it bounces off and this goes to this side. So the first question is correct, right? Not incorrect. Then if M1 is very large, then think about this is very large compared to M2. If they collide, what could happen? This moves to this side, pushing M2. So both moves to plus x direction. In that case, what happens? Second also is correct, right? Second one is also correct. If you don't understand, please let me know. Think about this is a very large object and this is a small object. Collide, what happens? Does this move backwards? No. This goes breaking this one, right? So both moves to plus x direction. Think about the extremes, right? Think that this is a very large object. Third one, M1 and M2 move both to plus s direction attached together. Third one is the wrong one. Okay, I'll explain second one again. Let's say M1 is very large compared to M2. So what could happen? Think like a train, right? A small car is moving in front of the train. No, the car is at rest. There's a train, right? And it collides. Does the train bounces back? The car and the train both goes to the same side, right? So same thing happens at the second option. Clear? You have to think that practically you cannot apply equations and it is very time consuming, right? So you have to have a way to remember these, what happens somewhat, right? This also is an exam question. Then the third one, this is very important, right? M1 and M2 move attached together. You have to remember this. after collision, if they attach, after collision, if they attach, these types of collisions are called inelastic collisions. Perfectly inelastic. At the previous recording also I have explained this. Perfectly inelastic. So this cannot be a elastic collision. So third one is the incorrect one, right? Remember that, right? In order to be perfectly inelastic, it doesn't have to stop. It just has to move attached together, right? To this side. After collision, it has to move attached together. Then those are called perfectly inelastic, not elastic, inelastic collisions. So this cannot be an elastic collision, right? In the question they say elastic. So the third one is the incorrect one. Got it? So third one is the answer there. Then then try 35th, 35, 35 question. 35. Let me know the answer. That's a usual question, right? 35. Let me know the answer there. Okay, let's see. So there's this bomb, 12 kilogram. Then it explodes, 4 kilogram, 8 kilogram. Uh, 8 kilogram gains 6 meters per second. 8 kilogram, right? Then 4 kilogram, let's say, gets V. So apply linear momentum to find V. So before explosion 0, after explosion 8 times 6 to this side minus 4 times V divided by 4. So V is equal to 12. 12 meters per second. What they ask is kinetic energy of this part. What's the kinetic energy? Kinetic energy of 4 kilogram, right? Half mass is 4, velocity is 12. 12 is squared. 2. 2 times 12 squared means 144. 288. Not kilojoule, right? Just joule. Correct? 12 kilogram velocity is 0, right? If it is not given, it is at rest. It just explodes. Understood? It is not given because it is at rest, right? Take it down. I think everyone understood that, right? It is not kilojoule, right? Just joule. Does not become kilojoule. Just joule, right? Kilogram and meters per square second, that is just joule, right? Okay, right. Then try 27. 27. That is a sentence question. Try that. 27. Okay, let's see what happens here, right? Trolley, it has a 5 kilogram mass, the mass of the trolley, right? Then water drops perpendicular to the trolley, right? So the velocity of water does not affect this motion. Horizontal motion is not affected by the velocity of this water. Velocity of, right? Let's see A. Momentum of trolley remains constant. Does it? So what's the momentum of the trolley? Before any water is added, momentum is what? 5 times 10. So that is 50, right? Because water is dropped perpendicular to the direction of this, momentum does not change. The force applied due to the water as it hits the trolley, there's a force applied, but that force is perpendicular to the direction of the trolley, right? So the momentum does not change actually. Understood? To this direction, momentum remains 50 kilograms meters per second. But the speed of the trolley drops. Why is that? To this direction, momentum does not change. So momentum is mv, right? Why? Because no force applied to horizontal direction. This remains constant, momentum, because there's no horizontal force. To change the horizontal momentum, there must be a horizontal force, but this does not have horizontal force. So horizontal momentum is constant. But as the time goes, what happens? The water is collected onto the trolley. So the mass is increasing. In order to keep the momentum constant, what should happen? The speed of the trolley has to drop. Understood? So A is correct. Momentum remains constant. It's true. A correct. B, after 10 seconds, speed of the trolley is 25/3. Let's see. What's the momentum of the trolley? 50. This cannot change. After 10 seconds, per second 0.1 kilogram of water is added. For 10 seconds, you have to multiply this by 1. Sorry, 10. 10 times 0.1 is 1 kilogram. So 1 kilogram of water is added. And already trolley has a mass 5. So now the total mass of the trolley is 5 plus 1, 6. A velocity is v. So what is this? 50 divided by 6. So it is 25 divided by 3. Velocity is 25 divided by 3. So B is correct. Got it? B is correct. Then they say kinetic energy trolley remains constant. Does it? Let's see. Half mv squared. Half, I'll just multiply. This equation also is very important, right? To find kinetic energy. Just multiply both denominator and numerator by mass. So this becomes m squared v squared divided by m. What did I do? Just multiply here by m and denominator by m. So this becomes half m squared v squared divided by m. Half mv squared, meaning let's say momentum is p squared divided by mass. So you see momentum remains constant. So this is another equation to find the kinetic energy, right? You might have seen this. E equals momentum squared divided by 2m. Got it? Later this will be very useful, right? This equation as well. So when we are doing matter and radiation, this will be useful. So we saw that momentum remains same. But what about mass? Mass is increasing, right? So the kinetic energy also should change. So remains constant is wrong. B is correct, but C is wrong. What about D? To keep the speed of the trolley constant, an external force is required. So as the time goes, water is collected to the trolley. So the speed is decreasing. To keep the speed constant, what do you need? You must have a external torque, external force. So D is correct, right? D is correct. Yeah, A, B and D. Yeah, that is the correct answer. A, B and D. Understood, right? If you need something to take it down, right? This equation, if you haven't seen this equation, please derive this and take it down, right? This is a useful equation. Then try 28. It is a similar question based on this theory. Try 28. 28. If you have done that, send me the answer, right? That is similar to the previous one, right? You have to apply the same theory. First you have to find the velocity here, right? Then you can find the change of kinetic energy. All right, let's see. Now listen, right? Now listen. So to do this, rain has to fall on the trolley vertically, right? If it had like a inclined velocity, then it is going to change the momentum, right? Then the question gets complicated, right? But here, due to the fall of rain, the momentum does not change. Okay, so let's see what's the momentum here. 5000 times 1.2, that's the momentum. Horizontal momentum does not change, so we can put a equal sign. Is equal to what? Here what's the mass? 6000. Mass changed, but the momentum did not, and the velocity is v. Okay, right. So 1.2 times 5 is what? 12 times 5 is 60, because zero point 0.2, it becomes 6,000, right? 5 times 1.2 means 6. Then there are 3 zeros and 6 cancels off. So V is 1 meters per second. If you didn't understand, let me know. This is the new velocity after collection of water. Velocity becomes 1 meters per second. Now what they ask is change of kinetic energy. So here, what's the kinetic energy? Let's say delta E, that is E1 minus E2. What is E1? Half, mass is 5000, velocity is 1.2 squared, minus here kinetic energy, half, mass is 1000, 5000, 6000, times velocity is 1 squared. Okay, then you just have to simplify this. I'll just take 1000 out from both. What do you get? 1.2 squared, that is 144, right? Divided by, multiplied by 5, divided by 2. Minus, here you get, when you take 1000 out, here you have 6 divided by 2. 1, 0.72. When you multiply that, 7.2 divided by 2, 3.6. Here you get 3. 3.6 minus 3, 1000. 0.6 times 1000. What is that? 600 joules. Yeah, correct answer. Delta E is 600 joules. Take it down, and if you have any questions, let me know. 600 joule is the change of kinetic energy. Previous question means 27, right? Okay, I'll explain that. I think you are telling about this one, right? Half mv squared. There's a useful form of this equation, right? There's a useful form of this equation. In order to make that, you have to multiply both denominator and numerator by simple m, mass. Okay? You can do that, right? Mass, it is similar to multiplying by 1. It is similar to multiplying by 1, right? M divided by m. You can do that. Then what do you get? Half m squared v squared divided by m. Half m squared v squared, you can take squared out and make it m. So mv means momentum. Momentum squared divided by half. So this is another form of equation for kinetic energy. This is useful, right? This is going to be useful. Because if momentum is constant, you can think about variation of kinetic energy with mass. This is just another form of useful form of the same equation, half mv squared. Is that what you're asking? Oh, did you under this is normally discussed when you're doing the theory, right? When you're doing theory, usually we discuss this one. Okay. I think everyone got this one, right? Got that? Right. So on the next class, next week, right? Next Saturday, I'll be doing work and energy. I'll start work and energy. Okay. So that is it is a very useful and important part, work and energy. I'll be doing a lot of questions on that. Hopefully there won't be any. We'll continue those classes without any interruptions there, right? From next week onwards, we'll be doing work and energy, because that part is very crucial. You must have a clear understanding of energy, because remaining parts of the syllabus also is based on energy, right? Those are different types of energy. So when you think about second unit, not second unit, third unit, waves and oscillations. In that unit, they are talking about energy of waves. Then the another unit, thermal physics, they are talking about energy regarding temperature. So all those units are energy, right? So to have a clear understanding of energy, you have to have an understanding of that mechanics part, energy in the mechanics part, work and energy, right? So I'm hoping to do a lot of questions to enhance your understanding of work and energy part, right? So from the next class, we'll be starting from that lesson, and you can let your friends know if they want to join that class. Okay, so that is from the next Saturday at 8 p.m. Okay, right. And if you have an issue, let me know. Right. Yeah, if you have an issue, please let me know after the class, right? Right. Okay. Then we'll wind up the class today from the Newton laws today for now. Then good night, everyone, right? Right. Sweet dreams.